Today's topic is brine line flow controls, what they are and how to set up the proper amount of brine for your system. Now, this is one of those little topics that's going to be actually fairly quick to discuss, but they're rather simple to go through. And we're just going to start off with some terminology and some component identification here. So what is a brine line flow control? Well, this is the brine valve. The brine valve is part of the brining system that literally, this is the traffic cop in the system. It's going to direct the flow between forcing water through the injector to draw brine out of the tank. And it's also going to move to force that same stream back into the tank to fill it. This is a diverter type valve, not a flow control. So this tells the valve where water should be going, not how much. The next component of the system is the brine tank safety valve. This is in the brine tank. This is not a brine line flow control either. This does not control brining at all. In very old water softeners, brining was controlled by a device like this in the tank, but they weren't very accurate. You'd have to size it, have a very accurate sized tank, and along with that, a very precisely, accurately measured float system to accurately measure how much water you have in the tank. Very complicated, could drift over time. This is no longer a brine control device. All this does is prevents overflow and switches the system over from brine draw to brine rinse.
I'm in the same boat. Let me know how it goes.
There we go. All right. Now, there is the brine line flow control adapter. This is typically located on the head of the valve. Here's the injector cover. This is the plumbing connection for the brine line coming from the brine tank to this adapter. This converts from a compression fitting to a standard thread sealed with an O-ring for either one of these style devices. So you have this adapter here. But this is where the brine line flow control lives. This is where it resides. This is where it's stored. And this is a very critical piece to the system. It's another one of those, few cent parts that are critical to the operation of a rather expensive water treatment device. So the brine line flow control. This is a washer that controls the amount of water that goes into the brine tank at a specific GPM flow rate. It's this hole. If you see here, you've got some standoff bumps here on some of them. Well, this needs to be inserted in a way in which you can read the numbers on it. That way, the flat side will make a proper seal when it needs to limit flow. And these bumps help keep it from sealing when you're drawing and allow full flow around this for the injector draw. So the water is going to go through this both ways, but it's only a control when there's water flowing into the tank. So the flow rating is stamped on this washer. It's a very small component. This can be difficult to read. Make sure you have a flashlight or a light source. And if you're like me, got to have your glasses on. I will quite often break out my camera on my phone, focus on it, and blow it up so I can read the numbers on here. Very, very difficult to do. Stamped black on black. We don't really want any paints or anything on it or dyes that may leach off into the water. That's the reason it's done that way. Sometimes problematic in a dark basement. but it's there for a reason. Break out a flashlight, take a look at what it's rated at. Because if you just pop in any washer, you're going to change the flow characteristics. So we want to match the stamp, the rubber stamp on the brine line flow control to the sticker on its adapter where it resides. These two should match. If they don't match, you need to understand the impact of changing that flow control into the tank. This is what controls the amount of water that goes into the tank based on what you program the valve to fill at. So essentially, the time you program into the controller for brine fill is the flow rate that goes through this device. So we have a complete line of flow controls offered by injector system size. For the 1600, this is a 3/8 inch line, all the way up to the 1650 brine control line control system. You have this available in 1.25 through 1 GPM flow rates here in the 1600 line of injectors. In the 1700s, these are the same ones that are used in the 1800. And you have a selection between 1.2 gallons per minute all the way up to 25 gallons per minute for very large brining applications. So there is a brine line flow control to match every valve in every scenario, allowing you to customize this process. So how much brine is enough? How do you program around this little inanimate device, right? Well, the basics of brining. The chemistry of ion exchange is dependent upon the source water chemistry. How much hardness, how much stuff are we going to exchange out on that cation exchange resin? The theoretical laboratory soak it forever kind of capacity of a resin is 40,000 grains per cubic foot. And this is just an industry average number. This isn't resin specific, okay? You may want to look at specific resins to look at capacities and fine tune your applications that way. Very general discussion here. To get this capacity of 40,000 grains per cubic foot, we would have to regenerate between 20 and 25 pounds of salt per regeneration. And regeneration follows this nice logarithmic curve where it rapidly increases in exchange and then it plateaus out. And you get very, very little benefit after a certain point by increasing the amount of salt you use. And that point is right around 15 pounds of salt. And that will give you 30,000 grains. And even at this point, we're starting to see diminishing returns on our use of salt as a regenerant. So this is kind of where the industry, through experience and research, has kind of drawn the line at the upper end. You may use these higher levels of salt regeneration in specific applications where you have specific water qualities that may require it. 15 pounds of salt per cubic foot. Places where I see that used is in heavy iron laden waters, waters that have a lot of +3 metals in them, like aluminum as a flocculant or things along those lines, that are more difficult to remove from the resin than hardness. And you may need more salt to remove that stuff to prevent it from falling over time. Now, the most salt efficient range is right around 9 pounds of salt per cubic foot. And this yields you 25,000 grain capacity. If you step down to 6 pounds of salt on that same logarithmic chart, you get about 20,000 grain capacity. And we're even seeing standards down as low as, in some municipalities, requiring as low as 3 pounds of salt per cubic foot of brining. That drops capacity down even more, that causes more frequent regeneration. So there's some balance there. They're really looking to limit salt concentrations going down the waistline. Iron, dissolved iron, not particulate, adds 2 to 5 grains per gallon of hardness per ppm of iron. And depending on your practice and water in your area, you may select that. So iron, 2 ppm of iron would equal an additional 4 to 10 grains per gallon of hardness that you would program. So if I had 10 grain per gallon hardness to start with 2 ppm of iron, I'm going to add 4 to 10 grains to that 10 grains per gallon and set my capacity based on that. 1 gallon of water dissolves approximately 3 pounds of salt. And the amount of water volume gets slightly increased when we dissolve salt in it. We're not going to be that specific in these sorts of applications. In high volume commercial applications, that may factor in to your decision-making process, but that's typically with brining systems that use delivery pumps instead of injectors to draw brine in, where it's more critical to be accurate with that. But for our purposes, 1 gallon of water dissolves 3 pounds of salt. So salt dosage determines the useful capacity of your resin. So here's a chart we've come up with, very general, based on salt dosing for cubic sizes of media and how much capacity you're going to have. And really, you can see that this is nothing more than a direct correlation in increase in amounts of resin. So everything with salt dosing, though, is going to be a function of 6 pounds for 1 cubic foot. We're going to need to double that for 2 cubic feet, 12 pounds, 3, 18 pounds, 24 pounds of salt. Because this is 6 pounds per cubic foot. Now, how to program your valve for brine filling is really based off of what you're going to brine at. That's up to you as a dealer or distributor. Where are you going to set that limits for that specific job? Well, let's say you're in Milwaukee, Wisconsin, where you now have a requirement to change over all valves from their existing brine line flow controls to an 1/8 of a gallon per minute brine line flow control. So if you had a 1 GPM flow control, brine line flow control in that unit, before you would have programmed for 6 pounds of salt, 2 minutes. 2 minutes to fill the tank, get your 6 pounds of salt, get your 2 minutes of water flow, get your 2 gallons of water, get your 6 pounds of salt. Well, to do that with an 1/8 of a gallon per minute, you're going to need 16 minutes to get that 2 gallons of water in the tank. So you'd be adjusting your programming from 2 minutes to 16 minutes when you switched from this brine line flow control to this one. So you're going to look at that sticker on the unit. If it's a unit you've never seen before, it may be worthwhile, and they're having some weird issues, to check to make sure that they have the proper flow control there. The reason for the 1/8 of a gallon per minute flow control change really has nothing to do with the brining process itself. It's about discharge standards and concentration of discharge. And that's really what they're looking to get brine efficiencies to. And they're looking at 4,000 grains per pound of salt. So it's about salt ratio coming out of softeners. They're trying to limit the amount of chloride discharge into the sanitary system, which eventually ends up in lakes, rivers, and streams. That's the number one thing about the change in certain municipalities. Minnesota's looking at making some of these changes. So if you're, I would suggest you get involved with your local WQA or other industry groups within your state and understand what's going on in your state, because these changes will happen with or without you. So be part of the discussion. So basically, this is about concentration going out and concentration coming back in, and brine efficiencies. They're really in these locations, they're regulating 3 pounds of salt per cubic foot, more so than the brine line flow control. But this is how they get those efficiencies at the setup, and that's what they want to see there. So remember this information for a cubic foot of resin. 6 pounds of salt for brining a 2 cubic foot of resin softener. It's 3 pounds per gallon of salt. We need 6 pounds of salt per cubic foot equals 2 gallons of water in this scenario. So 2 gallons of brine per cubic foot of resin. So 2 cubic foot of resin requires 4 gallons of water at 12 pounds of salt. So basically we took the water requirement for 6 pounds of salt and doubled it to get 12 pounds of salt into the brine. At 9 pounds and 3 pounds per gallon is 3 gallons of water per cubic foot. 2 times 3 is 6 gallons. It's just how you scale it up, going from 1 cubic foot to 2 cubic foot to 3 to 10 to 20, whatever.
So, noise hazards, distractions, are we isolated for those things? What does our workspace look like? Again, with ergonomic considerations being taken to.
So I'm going to go ahead and open the phone lines. Are there any questions out there?
Dave, I have a question.
Sure.
And you kind of answered it, but I'm still struggling a little bit with it. If you want 6 pounds of salt per which is or 6 pounds of salt per cubic foot to get the capacity you're looking for. Yeah. Go back a couple slides for me. This one here. Nope. Go back. There we go. Right there. So you're doing 6 pounds of salt per cubic foot, and you got different flow rates. And what changes is the amount of time.
Correct.
Okay. And you may have touched on this, when they're trying to cut down the lot, but if I do a 1/4 gallon per minute or a 1/2 gallon per minute, only thing that changes is how long I'm in the cycle time of the brine fill. Why would I pick one over the other? I mean, it's, to me, again, I'm being a little slow here because this is new. 4 minutes seems better. It takes less time to fill my brine tank up. I move on to the next cycle in the process versus 8 minutes versus 16 minutes. It still takes a couple of hours to make brine. That salt has to dissolve. Yeah. So I'm not getting the brine faster. I'm just spending less time in the brine cycle. Why do you pick 1/8 of a gallon per minute or a 1/2 or a 1/4?
They're doing that because they don't necessarily understand the ins and outs of this at a regulatory level. You're right.
Well,
the only thing that truly matters is how fast you draw it out of the tank.
What's the advantage they think regulatory by going to a slower brine generation? Do they think you're going to make less? I mean, you're not going to put less salt down the drain. You're not going to use less salt overall.
It ends up being a limiter in the system when you think about draw. The injector can only draw brine out through this around this flow control so fast. It's still a restriction. When it's to the size of the tank, it doesn't prevent that flow. They're just matching it down to small enough where somebody can't just pop another injector in and greatly increase it. So it's one of those standards that has, it really should just be controlled by the injector size to manage that. But what they're saying is we want this control in there so that we're going to either make this extremely long and painful for you, or you're going to program it the right way. And it's just sort of one of those technical nuances that doesn't have a whole lot of meaning, but it helps them manage the regulatory environment. So if they walk up and see a sticker 1/8 of a gallon permitted flow control, they know it should have been set up for that proper injector sizing as well.
Okay, but the brine line flow control really is in effect when you're filling the brine tank, not when you're drawing from the brine tank.
Correct. It literally, let's see if you get a picture of it. It literally flows.
Yeah, that's what I'm thinking. So it's not, I guess it has some effect because it's stuck in the line.
Yep.
Even though it's floating, water is going around it, it's not being controlled to that 1/8 of a gallon. You're still getting a lot more water, but you are restricting it somewhat.
Yeah. And yeah, it's one of those I kind of bang my head against with. It's like, this doesn't make a whole lot of sense. But what they're doing is trying to provide less wiggle room for people to get around the standard. And unfortunately, behavior control is part of regulation. It's not strictly technical control.
Okay. So by putting a smaller restrictor in there, you've got to use a smaller injector just because you are going to have some restriction to get that 10% brine solution that you're looking for, because you just can't suck it any faster. Even if the Venturi's opened up and you got theoretically higher flow coming in, the brine line flow control still affects the flow rate into your slow rinse.
Correct.
How much? Okay.
Yeah.
Okay, because it's not really designed to do that. It's not designed to control slow rinse.
No,
flow.
it's not at all.
But it does, just because you stuck a plug in the line. Even if it's floating, water's going about it, there is still some restriction there.
Correct.
Okay. Let's say they're trying to control my brining, and that doesn't really do it. I mean, it controls making brine, not using brine.
It's the combination of the two. And what it comes down to is most manufacturers of valves have these sort of paired in their valve selection. So they're just saying this is as much about human behavior control as it is about the actual technical effects. Because being technicians will make things work. This is one of the reasons if you're going out and finding unusual brining issues, you can't figure out why it's not giving you the right brine. Heaven forbid a technician ever just puts what he has on the truck in that fits, right? Because we've got 3 different brine line flow. Well, we got 4 different brine line flow controls that all will fit in this little housing, right?
Right.
If you don't pick it up out of your parts box and get it right, or grab the wrong one and don't double check, you're going to pop the wrong one in, and your programming is going to significantly change. If you put that half gallon per minute one in, you're going to get.
Yeah, you're running it for 8 minutes. You're going to get a lot more brine than you needed, and you're not going to use it all up. And eventually, you may overflow the tank.
Exactly.
Well, yeah, because you're going to draw. If you put twice as much brine in the tank, when you go into your slow rinse, you're going to rinse until all that brine is gone. So you're using twice as much salt as you need.
Absolutely.
So because the brine line flow control put too much water in the brine tank.
Correct.
And then it also affects your brine concentration when you're drawing brine, because it lets more. The injector is supposed to control that concentration. Yeah.
It won't change the brining ratio. It'll just take you a lot longer to suck it out of the tank, and you'll probably end up with salty water even after rapid rinse. And you're going to be going through salt like it's going out of style, all because of this little disc not matching up right. And that's one of those things, if you're a technician, that if you're walking into a situation where someone just purchased a rental unit, you may find out that you may have, there are some unscrupulous dealers out there that will bump up the next flow washer in and add too much water to the brine tank to sell more salt. So there's a lot of things there that there's potential skullduggery that can happen with this very small part. It's internal. You never check this thing unless you physically have to take it apart to either check it for a clog or something along those lines. Who's going to go in here and check this?
Right. So you want to make sure your drain line flow control is set up to work with the injector that you have in there, which is also programmed correctly to fill the right amount of water.
Yep. This is one of those things I would check on any new customer's valve I come across as a service. If I just get called out, this is something I would do as part of the evaluation, is check this out to make sure this is correct for what this sticker is and that it matches the programming.
Yeah,
because that way I put everything back to where it should be.
Because it's easy to, again, for newbies in this, which I'm one of those, it's easy to think, well, this controls how much brine is pulled out of the tank. And it really doesn't. It controls how much brine goes in the tank. The tank is always empty until the float ball hits bottom. So it does control how much brine you get, but it's on the other end on filling it versus drawing it.
Yes, absolutely. This is it's amazing how small parts regulate how well a softener works. Between this and the injector, you've got maybe $3 worth of parts, and without those $3, a valve is pretty much useless.
Okay.
These are the things that really govern the brining process, are the injector and this little button. And this is what will happen this is what will get clogged when you have foreign objects in your brine tank. We'll get into that. Is this little hole get plugged? Once that's plugged, you stop drawing, or you cut down the flow, or you won't be able to fill the brine tank.
Yeah, you'll get half the amount of brine you need instead of all of the brine you need. And it will still stop when the brine tank's empty. You just will not have regenerated adequately because you didn't have enough brine to do a good regeneration that you were expecting.
Yep. And this is between the injectors, the screens, and this. These are the most commonly plugged things after a new install, where if someone didn't backwash the unit long enough, or even, put it into rapid rinse and settle the bed, you'll get this plugged with brine, or not brine, resin or brine, foreign objects there as well. During the first startup, especially if someone's overfilled the tank with resin as well. So, there's a reason why we want freeboard in a tank, and it's so we don't plug up these sorts of components inside a valve.
So if it's all sized correctly, you can change your salt dosing simply by changing the time.
Absolutely.
And everything will work fine. You'll still have the right flow rates, the right draw, the right fill. You just have to put more water in and create more brine, and then you'll get a higher regen because you got more salt in there. Okay.
Yep.
That ties it all together.
This is the way cars used to be. They didn't used to have a settable choke. You just throw this disc in.
Yeah.
How is the flow control managed on the Logix and Auto Troll valve? That's actually, we manage it slightly differently. In the Auto Troll valve, that is adjusted the same way by restricting flow with a check ball and a slotted plug that goes in the head. So basically, we, instead of having a disc, we have a plug that has different slots in it that the check ball seals that cupped surface off and only allows a certain amount of water through that slot. And when we do the auto troll presentations later this summer, we'll talk about that. But we're limiting flow pretty much in a similar fashion there.
Yeah. It'd be like looking at this, and instead of the hole in the middle, it was a solid disc with slots cut around the sides that were sized to let a certain amount through. That's really what it is.
Yep. Yeah, it's just it's a different way to skin the cat. We're using a ball instead of this disc, where this disc floats back and forth. The ball floats back and forth, and it only seats when it rolls up and hits that cupped surface and allows water to go through the channel. Have a wonderful, profitable, and uneventful rest of your day.